Bismillahirrahmanirrahim. News labels 6 SSC2 Unit number 10 Simple Harmonic Motion and Wave. Today we will discuss mass spring system, ball and bowl and simple pendulum. Now, first of all, we know about what is meant by oscillation. Today we will discuss the oscillation and to understand the system that oscillates simple harmonic motion. Now, when a vibrating body, this is produced a type of oscillation, and the simple type of oscillation is called a simple harmonic motion. Simple harmonic motion is denoted by SHM. Now, we will discuss motion that repeats. In this diagram, we see that when the woman moves downward, the spring will pull up. The restoring force produced on oscillation, on bounce after another. So you will see many examples of systems with the restoring force that lead to oscillatory motion. Today we will discuss mass spring system. In this diagram, here you can see that now spring and restoring force. You learn that a stretch of a spring exerts a restoring force proportional to the stretch. So you have F is equal to minus K delta X, change in displacement. So, in this chapter, you will see how this linear restoring force lead to oscillation motion and what is the frequency determined by the spring constant K. Simple harmonic motion. In this diagram, we will discuss simple harmonic motion. In B part, the body of a mass M attached to a spring at a mean position O, where S is equal to 0. And when the force is applied, body moves the distance. The displacement is X. See in diagram A. When the block is displaced to the ring of equilibrium, the force exerted the spring X to left. And in B part, when the block is at equilibrium position, the force exerted by the spring is 0. Similarly, we can see that in C, when the block is displaced to the left of the equilibrium, the force exerted the spring at the right side. Now we will discuss periodic motion that regularly return to given the position after a fixed interval. Now, a particular type of periodic motion is a simple harmonic motion, which arrives the force acting on object is proportional to the position that of object about the some equilibrium position. So we can see that the motion of object is connected to spring is good example. Now recall the Hooke's law. According to Hooke's law, we can see in this diagram here node and antinode and why it produced. So we can explain Hooke's law states that restoring force F is proportional to displacement X. When restoring force Fs is equal to minus Kx, here K is a constant. So in this equation, Fs is a restoring force. Now it is always directed toward the equilibrium position. Therefore, it is always opposite to the displacement from the equilibrium. So K is a force of spring constant. Since X is a displacement, then what is the restoring force for a surface of water wave? Now we will discuss about more examples. Linear restoring force and SHM, simple harmonic motion. So in this diagram you can see that at equilibrium here no net force acts on it. When body in this condition, body in equilibrium condition at a original condition at a origin O, so no net force acts on it. But when a force is applied, body is displaced, so a displacement causes the spring to exert a force toward the equilibrium position. This force is a restoring force that toward the mean position. So we can see that if we displace a ladder attached to a spring from its equilibrium position, the spring exerts a restoring force back toward the equilibrium. Now we can see that F into net force is equal to minus AX. Why you use the negative sign? So the negative sign tells us that this is a restoring force because the force is in the direction to oppose the displacement. If we pull the ladder to the right, then X is positive. The force is that it moves the left, it will be negative, back toward the equilibrium. So, according to the Hooke's law, F is equal to minus Kx because this is restoring force. Now we will discuss about that motion of mass on spring. So we can see that here oscillation motion produced in a mass spring system. So in this condition, the point on the object that is measured. Here in this diagram, O is a mean position, A is a toward the left right, and negative A is the same displacement on left side. This is an equilibrium position at origin O. And here the displacement from this position. Now from body move to O to A. This graph is shows the solenoidal. This is the maximum displacement from left to right and right to left. So this is produce the simple harmonic motion when body oscillates between the to and fro motion. Now we can explain that the amplitude A is the object is a maximum displacement from the equilibrium and oscillation about an equilibrium position, what is a linear restoring force is always in a simple harmonic motion. Now, restoring force and the mass spring system. We can explain in this diagram, we can see that body at a original condition O, no net force act on it. Fs is equal to 0. But when the body moves diagram and cover the displacement x, then restoring force toward the mean position. And similarly, it is true and slow motion between point A to point B. So we can explain that in this block, the displacement to the right of x is equal to 0. The position is positive and the restoring force is directed toward the left is negative. Similarly, we can see that in a block B part, the block at an equilibrium position, so x is equal to 0. When in a B part, the spring is neither to stretch or not to stretch, so the force F is equal to 0. In this case, C, we can see the block displaced to the left. The position is a negative, so the restoring force is directed toward the right, will be positive. Now we will discuss that acceleration. What is the acceleration? Note that the acceleration is not constant. Unlike our earlier quadratic equation. So, if the block is released from the position x is equal to a, then the initial acceleration is minus ka over m. But is passed through at a origin O, then acceleration will be false and to be decreases from 0. Now it is only continue for it is equilibrium point because it know the momentum and kinetic energy carries on the past x is equal to 0. The block is continued to x is equal to minus a. This will be acceleration will be positive. So a is equal to ka upon m. Transfer of energy in a simple harmonic motion we can see in this diagram. At a mean position, total energy is a kinetic energy. At a extreme position, total energy is a potential energy. But energy remains constant. In either we can see that K is a kinetic energy and U is a potential energy. K plus U is equal to constant. So we can explain that at this diagram or this color is a potential energy and this color shows the kinetic energy. You can see that potential energy is equal to 1 upon 2 k x square and kinetic energy is equal to 1 upon 2 mv square. At a mean position, maximum speed, so at a mean position, maximum kinetic energy, potential energy will be 0. At a extreme condition, speed is minimum, so potential energy will be maximum because it covers the maximum displacement, so x square will be maximum, total energy is equal to potential energy and kinetic energy will be 0. Now you can see that total energy is constant at all the time and proportional to the square of the amplitude. Now you can write that energy is continuously being transferred between the potential stored to the spring and kinetic energy of the block. Now energy in a simple harmonic motion. Then you can see that in this diagram at a mean position total energy is a kinetic energy and at a extreme position total energy is a potential energy and between them energy will be varied. Why the mean position energy will be maximum? Because at a mean position due to the restoring force speed will be increased. So at a mean position kinetic energy will be increased. At a same position distance will be increased. So according to the displacement potential energy will be increased and kinetic energy will be decreasing. Now in this diagram you can see that at a O position E is equal to energy is equal to kinetic energy plus potential energy and at a position potential energy will be maximum and kinetic energy will be 0. Similarly, we can see at a negative point minus a energy will be 0 and potential energy will be maximum. So we can explain that at a mean position total energy remains constant. This is the energy conservation in a simple harmonic motion SHM. Now we will discuss that simple harmonic motion in a spring oscillation. So you can see that again in this diagram at a mean position x is equal to 0. When force is applied, it will move the displacement x and produce the restoring force F. This is toward the mean position and in C diagram this move toward the left and restoring force toward the mean position. In the spring system, body is oscillating between main position to extreme position and extreme position to main position. So, an object vibrates, oscillates back and forth over the same path. Each cycle takes the same amount of time. The motion of is called the period. The mass and spring system is useful for the periodic system. Now we can see that in simple harmonic motion, we can discuss that we assume the force of frictionless. The point of the spring is neither stretched or nor compressed. The position of this is the equilibrium. This is measurement is equal to the displacement at a mean position x is equal to 0. We can see in a previous figure. So here we can see that simple harmonic motion is depend upon two things. Body is shows the inertia and other is obey the Hooke's law, but depend upon the four things: fractionless, obey the inertia, and body is contain the force, displacement, and body moving toward the mean position. So the force exerted by the spring depend upon the displacement. Now here we can see that F is equal to minus kf by the Hooke's law, force exerted by a spring. Simple harmonic motion in a spring system, so we can use the minus sign, the force indicating the restoring force, and direct it toward the mean position. So mass is in equilibrium condition. Here K is a constant and it is called the spring constant. K is called the spring constant and similarly the force is not constant. So the acceleration is not constant because force is directly proportional to its displacement. So it is a not constant, it varies. So acceleration is not constant, it is depend upon the force, but it is always directly proportional to its displacement. So according to the simple harmonic motion. Now simple harmonic motion shown in this diagram. Here we can see that at V is equal to 0 at a extreme position. At a position, negative A position, velocity will be 0. But when we will move toward the main position, velocity will be increasing at a position O. Region, velocity will be maximum and at the other extreme position, velocity will be 0. Now, when it will move toward the main position, velocity will be maximum. So, this is a pro and flow motion between two points, but it is always directed toward the main position. So, we can see that displacement is measured from the equilibrium point and amplitude is the maximum displacement of the body of the measurement. So a cycle is a full to and fro motion. In this figure we can see that the half cycle of moving displacement of SHM. Now, the period is the time required to complete one revolution is called one cycle. So, frequency is the number of cycles complete per second. Now, simple harmonic motion it shows that a vibrating system where the restoring force is proportional to the negative of the displacement is in simple harmonic motion SHM and is often is called a simple harmonic motion. So you can see that the restoring force is directly proportional to the displacement and it is always directed toward the mean position. Because directed toward the mean position due to the restoring force we can show that it is a negative sign. We can use the negative sign for a restoring force. So you can see that the time period of the SHM, therefore you can Use the period and frequency of particle moving in a circle to find the period and frequency. So T is equal to 2 pi m upon k whole cube and frequency f is equal to 1 upon t, that is equal to 1 upon 2 pi k or m. So frequency and time period are reciprocal to each other and this relation is shown in this equation. And shown in this equation, and we write that both equations are related to each other. Thank you. Best of luck. Allah Hafiz.